number 57, that's due today.
Uh-huh.
The curve, like, didn't intersect with the system curve.
One of them did,
Yeah.
right? Yes.
So how would you find your operating?
Well, so let's kind of walk you through it. If your system curve and your pump curve, there is no point. So what, I mean, intuitively, what does that tell you, Lauren?
That it doesn't operate?
What's that?
It's not operating on that curve?
It's operating, but the pump is pumping, but there's no flow.
Okay.
Okay? So think about it in this concept. If you have two tanks that are 100 feet apart, and you tell, the contractor, go out there and put a pump in there, and the contractor grabs the wrong pump and puts in a pump that'll pump 90 feet ahead. Okay? What's going to happen? The pump, you turn the pump on, the pump's going to go, but it's not going to pump anything. It's going to try and lift it up there, but it's trying to push something up higher than it has the ability. And so there's going to be no flow. In fact, if you don't have a check valve in your system, the water is going to flow back through the pump backwards, which is not a good thing. That's really bad for pumps. Unless they're designed as a pump turbine, then that's a different story. So the question to the whole class, what happens if you have 100 foot ahead and he puts in a pump that is designed to add 100 feet ahead? That's the shutoff head. What happens then? Yeah, you may have a drop come out, or you may have a drop go the other direction, but nothing. Now, as soon as he puts a pump with 101, then you're going to get a little trickle. But yeah, so if you turn your rotational speed down on a pump, on a variable speed pump, you can turn it so low that yeah, it's just not producing any flow whatsoever. Okay. All right. So for those that didn't get their exams yet, I have been pretty busy the last couple of days, and I didn't get any time to scan those in. So I'll do my best. It's a busy day today too, so we'll see what we can do, but I just need to get over to the office and ask them to do it for me. Is anyone here that didn't pick up their exam yet? You got everyone? Okay, yeah, I'm thinking that, all right. So I do have them with me here. Let's see, what am I doing? Let me just share my screen. All right. Okay. So I want to give you an example then of a pipe network with a pump. Okay. Network with pump. Imagine, if you will, we've got a reservoir over here, some elevation, we'll define that in a minute. We come to some pump right here, and then we continue over to a pipe network, and I'm going to make a simple pipe network. Now let's keep it really simple. Okay, and we'll call this 1, pipe 2, pipe 3, pipe 4, pipe 5, pipe 6, pipe 7, pipe 8, and pipe 9. All right. Let's go ahead and give some values to this. Let's say that this reservoir A over here has a value of 20 feet. Reservoir B over here has a value of 120 feet. And our pump has a total dynamic head of let's do this, 120 plus 0.05 minus, or times Q. Minus 0.02 Q squared. So that's our pump equation. Okay. And to make life simple, we can even say Q is unit-wise in gallons per minute. Because my goal here is to show you the concept of putting this in a spreadsheet. I'm not going to actually work the whole spreadsheet, because you already know how to work the whole spreadsheet, right? Let's just kind of do a quick review. We've got this situation here, and we know that we have how many unknowns that we're trying to find? Okay, well, let's first talk about the number of unknowns, and then we can come back and define those. Because you're right, we do have one pseudo loop. But we have how many? 9. And how do you know that? 9 pipes. Right, good. So the unknowns is 9. So we want to find flow rates 1 through 9. We got told that we have one pseudo loop, and I'm going to assume a clockwise direction for the pseudo loop. And how many loops then? 2. Okay, so we have loop 1 right here. Once again, assume a clockwise direction, and clockwise direction here. So if I have 9 unknowns, and I'm going to take off 2 loops and 1 pseudo loop, that leaves me with 6 continuity equations, right? And fortunately, I have 1, 2, 3, and put a 4 down here, 5, and 6 nodes. So plenty of nodes for continuity, plenty of nodes or energy equation, pseudo loop to solve this problem. All right. So I'm going to make the assumption that the first 6 equations that I'm going to write are going to be my 6 continuity equations. All right. And then I'm going to make the assumption that my next 2 are going to be my loop equations. So equation 9 then, when I write equation 9, which is my pseudo loop, okay. Oh, did that, sorry. I was thinking of the one control hole, but yeah, didn't even look. Thank you. That might make it a little easier, right? All right, and it's going to remind me to do that too. Okay, so to write my pseudo loop then, I'm going to start off with my hydraulic grade line at B, and I need to define the direction of flow. So I'm just going to define, I'm going to say the pump's going to come in here, and I'm going to put them all positive just to make life easy. Going over to B, all right? So now I can write this as the hydraulic grade line at B, assuming that I'm going against the flow. So now plus C sub 4 times Q sub 4 squared plus C sub 3 times Q sub 3 squared plus C sub 2 times Q sub 2 squared. And then I get over here to pump or pipe 1, and I know that I'm going against the flow on that as well, plus C sub 1 Q sub 1 squared. All right, but I have to take care of that pump as well. So remember how we drew the hydraulic grade line. So when I'm approaching it from the right, what happens when I hit the pump? I drop down, right? The hydraulic grade line went to the pump, then it jumps up at the pump and continues down if I'm going with the flow. Well, now I'm going against the flow. So I'm adding the energy back up, but then when I hit the pump, I drop. And then I finish going to the reservoir. So this is going to be minus H sub P equals then the hydraulic grade line at A. Now, of course, I can come in here and say, well, I know the hydraulic grade line at B is 120, and I know the hydraulic grade line at A is 20. And I know the head of the pump. The head of the pump is the total dynamic head up there. So I can actually bring this term down here and write minus then in the brackets 120 plus 0.05 Q sub 1 minus 0.02 times Q sub 1 squared, end of the bracket. So I'm just putting that equation right in there, and I'm letting the negative sign go throughout the whole thing. Okay? So now when I go to build this, I'm going to have a 9 by 9 matrix with my flows Q1 all the way on down to Q sub 9. And that's going to equal my B vector then. Whoops. Of course, the top ones are going to have either 0 or the demand over here. But once again, I'm not going to worry about all those. When I get down to the energy equation, the energy equations are 2 zeros. And then this last one here, I have to determine what's going on over there. Okay? So this is the part you already know how to do. You know already how to fill out all these. There's my 6 continuity equations. Here's my pseudo loop 1. Here's my pseudo loop 2. And now I want to fill out my pseudo loop. Okay. Specifically, I want to focus on this spot right over here, pipe 1, because the other pipes are all the same. You've done all those before. In fact, if we had minor losses, we've done that too. You know how to put minor losses in there. So the only new part is this pump. Okay. So using those values, let's go ahead and let me give a value. Well, no, I guess we can keep C sub 1 there. So now, when we put this value in here, we're going to grab these two terms. All right. So I'm going to have C sub 1 times Q sub 1. Should I call it old or prime? You guys care? Prime, okay. Q sub 1 prime. And then I'm going to have minus 120 plus 0.05 minus 0.02 Q sub 1 prime, end of bracket, and then this whole, oh, I did that wrong, didn't I? Yeah, I didn't use my eraser pen. Sorry. This bracket shouldn't be there. Actually, I need to start this whole thing over. I kind of messed it up, didn't I? Tell you what, let's do this. Let's rewrite this equation. C sub 1 times Q sub 1 squared. And I'm gonna put the negative sign throughout there. So minus 120 minus 0.05 plus 0.02 Q sub 1 squared. All right. Okay. Oh, I do, yes. Q sub 1 right there, thank you. Start using an erasable one so I can fix it. Okay, so now when I'm looking at this, I do know that this value is not impacted by a variable. Okay, so it's going to go over to the other side and it's going to become 120 positive. And now I can go ahead and take the remaining terms and group those then as C sub 1 times Q sub 1 prime, okay, minus 0.05 plus 0.02 Q sub 1 prime, and all of that will be multiplied by Q sub 1.
Are these the primes? Are they still absolute values?
Yes, so when we put them into Excel, then we're going to put the absolute values in there. Yes, that's a good point. I do want to highlight the fact that we should know the direction of the flow in the pipe we put the pump in. So technically speaking, we wouldn't need them, but it's a good practice. I think I mentioned this last time. Okay. The other thing I wanted to highlight was that this Q sub 1 here is actually the Q sub 1 up here. That's what we're trying to solve for. So when we put this into our spreadsheet, yes, then we're going to go C sub 1 times the absolute value of Q sub 1 prime minus 0.05 plus 0.02 times the absolute value of Q sub 1 prime. Okay. Now, if you want to get fancy, you could combine like terms, right? You could say C sub 1 plus 0.02 times the absolute value of Q sub 1 prime minus 0.05. And this thing right here is what would go into that cell right there. Okay. So really nothing different than we talked about last time. We just put some numbers to it. And now we come over to our B vector. Okay. Going back to our original equation, we've got 120 over here. So I've got the HDL at A minus the HDL at B plus that 120. So noting that A is going to be 20 and that B is going to be 120. Well, I didn't plan those. I guess I did plan those. I didn't think about that when I set this up, but ultimately then, you know, the 120, the 20 is going to cancel out. So what would go in this cell right here would be 20. That's the value that would go there. And it would not change because we're assuming that we're taking a snapshot in time and that our water levels are fixed. Now, this is a steady state analysis. If we went another step and started doing unsteady, then we'd have to track the volume of flow going into the tank, how big the tank is, and how fast the water level is changing. All right?
Dr. Savage, I have a question.
Sure.
Can you explain why, like where you plugged that equation into the matrix, why it isn't on the same line as Q1?
Okay. Why is
it that, and then in the B matrix, it's Q9 on the same line?
Okay. So if we come back to our loop, and if I was to put the first node equation to get, if I was to write the first continuity equation, all right, so I'm looking at my continuity equations here. I would have, I'm gonna have to make another selection there, but at node 1, I'm gonna have Q sub 1 minus Q sub 2 minus Q sub 5, and let's say there is a demand there. Let's put D1 there, a demand coming out. Minus D1 equals 0. That's my continuity equation at node 1. Are we comfortable with that?
Yeah.
Okay. Okay. Good. So now remember that we want to put these equations into our matrix. So if we were to do matrix multiplication, we would get the equations back. So my first line right here, the coefficient out in front of in front of Q1 is 1, and in front of Q2 is 1, and Q5 is 1. So over here in my matrix, I'm going to have 1, 1, 1. This is the spot for 3, this spot for 4, spot for 5. Well, let's see, 2 is going to be a -1, yeah. And then the spot for 5 is going to be a -1. The spot for 6 is going to be 0. The spot for 7 is 0. And the spot for 8 is 0. And the spot for 9 is 0. Did I do that right? Yep. So if you remember in linear algebra, when you have a matrix like this and your solution vector, if you bring the solution vector up on top and write this as q sub 1, q sub 2, all over to q sub 9, and then you bring it down and multiply it by the values in this row, you're going to end up back with your original equation.
I'm with you now. That makes sense.
Okay, all right, so, oh, good. Okay. All right, any other questions on setting up this matrix? So you should now have the ability to solve the homework problem. All right, it's the homework problem that you did without a pump. The reservoirs have changed elevations and you're just adding one pump in. And so you have to modify a few things. For some of you, it'll go really easy, and some of you that get a sign wrong, it'll drive you crazy, right? But you have that ability to do that now. So see, give that a shot and get that done. All right, so with that, we are going to kind of leave pumps and networks for a little bit. We're kind of going to head off in a slightly different direction and potentially come back to pumps at the end of the semester when we learn the software package. Now, there has been a little glitch, and they tell me that they're supposed to be working it out so we can get the software package, which is called WaterCAD, available for you to download onto your laptop or your home computer and use it when you're not on campus. I'm going to vent here for just a little bit. We just got, by the way, you know, I've been waiting to get this thing resolved. I just got an email this morning. We have purchased MathCAD for the civil students. Now, does anyone in here use, I don't know if I've asked, anyone here use MathCAD? So Zach's used it. MathCAD's a rather interesting software, and we're going to try and incorporate it into the civil tools this semester. But it's kind of cool, right? I mean, you can see, you write your equations as you would see them in a math book, and then it'll solve them for you. And so a lot of consulting firms are starting to go the route of setting up design sheets inside of MathCAD. And all you do is go in and change some parameters. So it's like Excel. You can set up Excel to do the same thing, except from now you can see the equations and you're not just seeing all these numbers and wondering what equation is in that cell. So it's a little more visually interactive. And it'll integrate, it'll differentiate symbolically. I mean, it's really kind of cool. It's so it's like MATLAB, except for the programming capabilities are not as easy as MATLAB. And MATLAB, if you want to solve a problem, you have to write these little scripts. And it's kind of, Zach's shaking his head, kind of a pain in the butt. So MathCAD is very nice in that sense, and it's a great tool to learn, but it is kind of pricey. Some, like I say, some engineering firms are going to it, others are saying, no, it's too pricey. So we bought this software. We had an old version that we had a license to, but it was really old. We completely changed the format. And it's not cheap. And so, but we did get the academic discount, which is a little nicer. And they have a free version, the student version that's free, but the capabilities of it are not great. So they send this to us, and then it's called, we call Node Lock.
In other words, we bought 25 licenses, but those 25 licenses had to be installed on 25 computers, only for those 25 computers. And here we are in the middle of COVID. It's like, well, whose 25 computers are we going to install these on, right? We want to start making this available to all civil engineering students. Well, this is stupid. You got to have a license that students can check when they get onto MathCAD, that they can go check out the license, use it, and when they're done, the license goes back for someone else to use, right? So they're like, oh, that's going to cost you extra. Whatever, just pay the extra money. So we get it. Well, now, yeah, it works that way, but guess what? You got to be on an ISU computer or have a VPN access to get it. I mean, and the IT guys have said, well, we can work around that, but we can't install it till after the semester because we got to do a complete shutdown and reboot the server and everything. And I'm like, so the students in civil tools that were trying to learn this too, you're telling me that we're telling them that they got to come to class now, when the whole semester we've been telling them they don't have to, they can do it at home. And now you got to come, and it's like, that just makes no sense, right? Anyway, thanks for being my therapist. Appreciate it. I feel better. Now we can move forward. All right.
Actually makes it perfect. If you know software salespeople, it makes perfect sense.
Yeah, it's really kind of sad that, especially now when we're trying to make things a little more accessible for students at home. We'll get it figured out. All right, so what I want to jump to now then is, let me bring up Moodle, because I posted these documents on Moodle. Okay, so 3 documents. So we've been talking a little bit about pipe networks, and that's all great and everything. And you can calculate the numbers, but the harder part is trying to decide what are the demands, what's going on in your pipe network, and how do you account for that, okay? So I put these documents on there, and as part of your homework, it's going to be to read through these documents. They're not very long, but I would briefly want to skim through them, all right? So as a practicing engineer, if you start working on a city system, whether you're working for the city or for a consulting engineer that's working for the city, you're going to have to look at these different components of a water supply system. The source of the water. Is it coming out of the ground? Is it coming out of the surface? Around here, we're pretty lucky that we can pull water out of the ground, aerate it to get to some of the dissolved minerals to fall out, throw some chlorine in it and put it in our system. But there's a lot of places around the country and around the world where you can't do that, where you have to have a water treatment system. You're going to pull water out of a reservoir, out of a pond, out of a river, and it's going to have all sorts of stuff in it, and you have to clean it up enough to be able to put it in the water system. So you got to identify the source, and then you have to have enough storage in the source, all right? Now the storage is not just storage of untreated water, you have to have sufficient storage for treated water. And the question comes up, how much storage? Well, that's not always decided by engineers. We kind of have some rules of thumb. You know, you want to make sure you have enough storage for the peak day. You're like, what's the peak day? Well, we'll get to the peak day. In essence, well, I can just tell you essentially, it's what is the most water used during the highest time of the year. You know, you don't want to run out of water. If you have enough storage for the peak day, then you're good, right? But what happens if a fire occurs on the peak day? Well, you have to account for fire flows too, and we'll get to fire flows. So you got to make sure that you have a sufficient storage to account for all that. Now you have to account for the transmission. Oh, and I guess I'm getting ahead of myself here, kind of lumping a couple of things. So the transmission is from the source, the storage of the source, the transmission, then the treatment, and then the distribution, okay? You got to send it out. We've primarily been focusing on what, if you thought about it, the distribution going through a pipe network, but we've also been doing single pipelines, and that's nothing, that's the transmission right there, okay? And in Dr. Sato's class, you do the treatment. And actually in the source, we talk a little bit in the water resources class, not a lot, but just kind of, we talk about routing water through reservoirs and so forth and how much storage you need. So within the program here, if you take all those courses, you would get all 5 of those things, all right? But I want to focus on how much water is needed. So going back to this distribution, how much water do we need, all right? Because you just can't say, all right, I'm just going to count up the number of people and how much they use each day and boom, I'm good. Because you have industry, you've got agricultural, you've got industrial processes, firefighting, lawn use, so that's kind of irrigation in a residential sense. And if you was to guess how much, let's take the irrigation out of it first. So how much water, on average, in the United States, does one person use per day? Not how much is attributed to one person saying, well, we have to have water for forming these tires up, and people use tires. I want to talk about personal daily use. The average use for brushing your teeth, cooking, doing your laundry, showering, doing all those different things, no irrigation of your lawn or anything like that. How many gallons a day do you think you use on average? Or the average person? Whatever the average is, right? Who defines average? But any ideas? Take some guess. In gallons. Let's throw it out in gallons. 40 gallons. So we've got 1 for 40. Any other thoughts?
I would probably say closer to 20 or something.
Closer to 20, because 40 sounds like a lot, right? Like, geez, how long showers do you take? Other thoughts?
Got a bathtub for 9.
You got a bathtub that holds 9?
No, it was a bad joke. It was a bathtub for 9.
Oh, okay. All right, no other thoughts? Anyone online want to throw out a guess? By the way, can you guys online see this? I think I forgot to share. You guys haven't said anything. Let me, where is that document? Oh, there we go. Okay, maybe you guys could have seen it. Do you see that? All right. Surely someone online wants to throw out a guess. Surely someone online has typed into Google how many gallons, right? So I haven't checked for a couple of years. 95 to 100 gallons per day, per person. 95 to 100 gallons per day. Yep. Now, we use a term per capita. If you haven't heard that term before, that means per person. So 95 gallons per day per capita, okay? Or 100, depends on. Now, it gets even worse. If you come back out here to the west, and you include irrigation of lawns, not farm irrigation, not food production, but irrigation of lawns. And if you include washing cars and things like that, you're about 220 gallons per day per capita for the whole year. That's the average use every day. It's a lot of water, right? Now, obviously, people who live in bigger homes and bigger yards tend to use more water than people who live in tiny houses or apartments, right? On average, there's always exceptions, but on average. I mean, I can see someone living in an apartment complex that has a hot tub out on their balcony and they like to change the water every week or so. They could use a lot of water. So there are changes to that, but that's the average. Now, as an engineer, if we're working for a city, we just can't say, hey, I'm going to design a system that's going to meet your needs now. All right. New subdivisions going in, and well, we need a little more water storage, so we're going to put this water tank up on the hill. Well, that's great, but what about in 2 years, or in 10 years, or in 30 years? Are you going to have to, start putting these small little tanks everywhere? So you have to decide, what is the life cycle? How far in the future am I going to build for? And put that all together, okay? And if you're really good, you probably would be an engineer, you'd be down in Vegas, right? Making these types of guesses. Sometimes it's hard. For example, the city of Chubbuck. They said back in 2008, we're going to expect a lot of growth because there was a lot of growth in Chubbuck. And so we're going to put in a sewer collection system and also expand our water lines, but mostly it was on the sewer side. And so they went in and they bonded, you know, if you're not familiar with bonding, basically they say, we're gonna go out and get some money to be able to build this and raise your taxes a little bit so we can pay this loan off, okay? So we're gonna put it in right now, and the bonds tend to get really cheap rates, interest rates, but we know we want this infrastructure now, and then our citizens will pay it off throughout the coming years as we retire the bond and we pay the bond off. So they did this. They put in a nice sewer lift station, collect where they thought there was going to be a lot of growth. And then what happened? The economy tanked and the growth did not happen. And they're stuck with this really nice system that they had to pay for. And so the sewer rates inside the city of Chubbuck went sewer and water. I think they kind of coupled it with water, are really high. Now, here it is 2020, 12 years later, the growth is happening. It's not like they went completely wrong because they knew the growth was going to happen at some point. It just didn't, they thought it was going to happen then, didn't happen then, but it is happening now. So there's a whole lot of growth going on out in that area. And I know that because that's kind of the area that I live out in. So they're gonna get all this coming in. And the system is going to get, the point is it sat for 12 years based on someone's prediction, whether it was the engineer, whether it was the city mayor, whether it was the city council or the city planner. Someone predicted, well, we got to have it now because it's coming. We need it, you know, we're going to need it in 3 years. Well, 12 years later, they need it. Now, I'm not trying to point that out as a bad decision. I'm just trying to point out that we take our best shot. We use our best value, our best judgments, and sometimes we're not right. Okay. Now, hopefully on the technical side, we're right, but on the planning side, it's a little harder to do that. All right. Kind of scroll it down here. What is the demand that we need to plan for? The demand is going to be the rate of use times the number of users. Makes pretty good sense, right? How much water per day on average are we using? How many people do we have? But wait, we have to plan for the future too. How many people are we going to have in the future? If we want this system, we only want to put this system in once now, and then we want it to last for 20 years. What's the capacity? So we're going to have some population estimates, some growth estimates to add into that. Okay. And this talks a little bit then about the domestic demands. What changes the domestic demand? Well, it could be the climate. Warm climates tend to use more water than hot. Than cold. Hot climates, yeah, versus cold climates. Standard of living. Extent of the sewerage. If you have a sewer system, you tend to use more water. What is the pressure in the system? If you have high pressure, you tend to use more water. Quality. People think that the water stinks and they don't want to use it. And then the cost. Cost is kind of rather interesting because it's generally fairly inelastic. You guys remember that term from economics? What does inelastic mean?
Like people are willing to pay whatever based on the price.
Yeah, it's kind of like they don't give much thought to the cost of it. There's some goods like salt that you only buy every now and then. You don't care if it's $1 per thing or $5. You're like, oh, I just need salt, right? Because you only buy it every so often. Well, water is kind of the same way. Well, I need water. And it's not until the price gets up to a certain point that people start thinking about, wow, I need to fix that leaky toilet. Wow, I need to fix that drip. Because now it actually starts to be so high that it impacts them. And, you know, we've been very fortunate in this country where water's been relatively cheap. Not always so in other parts of the world. All right. I'm going to diverge for just a second. So I had a graduate student, a master's student, who was from Bangladesh, the city called Dhaka City. Anyone heard of Dhaka City? Okay, one person online. I can't see anyone raise their hand out there, so I don't know, maybe a few of you have. I hadn't heard of Dhaka City before I had him. I'm Bangladesh, I know where that's at. Dhaka City, probably the 4th or 5th largest city in the world. It's like, whoa, really? Yeah. Ranks up there with Mexico, you know, New York, Houston, some of the others, you know, Singapore, Hong Kong. I mean, just huge. 15 million people in the city. Okay. Very poor country. And his work, he wanted to study how to clean water using locally available materials, because inside of Dhaka City, there's these slums. And the people are, unfortunately, even the water is provided by the government. They don't really have a lot of private practice over there, and so they have what they call a standpipe, which is a little different over here. A standpipe is a tank, over there a standpipe is a water faucet. And they have this water faucet that has water a couple hours during the day, and they take all their containers over there and fill them up. But unfortunately, even that water is not always good quality, even though it comes from a water treatment plant, because it goes to a slum. All right, now imagine this. I don't know if this has any relevance to you, of how big is 100 acres. Okay. I grew up on a farm that was essentially 100 acres. How would you describe how big is a couple hundred acres? It's not more than a couple city blocks. A city block is usually 40 acres, a full city block. So 2.5 city blocks, if you will. 200,000 people living in this slum. And there's multiple slums around the city. So he had one slum that he picked out, Coriel slum, and there's a river going through the slum, and the river was used by a lot of industry, and so water wasn't very clean. And they had some of their wastewater facilities were just latrines hanging out over the river. So the waste would just drop into the river. They would use the river for bathing, for washing clothes, and some of them use it for drinking water. I mean, it's pretty sad. You know, it kind of tears your heart a little bit to read the description when he was describing the place over there. But they have a lot of clay. And so he was saying, you know, you can take this clay, and if you construct it right, you can create 2 flower pots, and you put water in the top one, and then throughout the day, the water drips down into the bottom one, and then you have relatively clean water. And they have filters for that, ceramic filters. They're really, really good, but the people would have to work for a month, take a month's worth of salary to buy one of those ceramic filters. And he was saying, you know, if we could build these clay pots for a couple days' wages, then the people would have clean water. And if you have clean water, then you have better health, because a lot of the diseases that they were dealing with is due to that. And he found that it worked. And he's not the only one proposed it. He had a kind of a unique configuration and wanted to test the exact soil makeup near Dhaka City, and so he was able to build the pots out of that exact clay. And it wasn't perfect, but it was pretty good. You know, it was a pretty good idea. And you put sawdust inside the clay, and then when you fire the clay inside the kiln, the sawdust burns and actually becomes activated carbon and provides the little holes. And then the water, as it drips down through there, the bacteria attach to the activated carbon, and it acts as a filter as well. So, you know, kind of cool. Once again, not perfect, but better than nothing. So, you know, kind of help me appreciate the value of what we have here and in other developed countries. Sometimes we get a little bit, take those things for granted of how nice it is to go turn on a faucet and have water come out. Okay? Not everywhere in the world has that. Okay. So in here, we talk about some peaking factors, okay? And I'm just going to highlight these really fast and let you guys read these on your own and kind of write them down. But we have these maximum day ratios. What is the highest day of the year? How much is that highest day over the average day? And it's usually from 1.5 to 2.5 times the average day. All right. And then we also have the peak hour range that says that the average hour throughout the year, the peak hour, which is generally in the summertime, is 3 times as much as the peak hour or the average hour at any other time. But we take that as the average of the day. So we're gonna start on Monday, start talking about the annual average daily flow and the maximum daily flow and the peak hourly flow. We'll throw all these terms around. But these are good rules of thumb or good multiplication factors that help us figure out if we've got a certain size of a population, how much water would we may need, okay? Now I would tell you the best way to figure this out if you're dealing with a city that's already exists is to go get their water records and say, what is your average annual daily flow? And they should have that now. They should be metering their water. And so if nothing else, you can track what is their average flow, and then you can use the peaking factors. But if they have really good data, you can actually calculate what is the peaking factor. And if you're adding a new subdivision, we got Northgate going on, north of town, you can say, well, this is what the city of Pocatello or the city of Chubbuck uses now, and we expect this growth to be very similar to what we already have, because we're going to put in houses that are similar to what we have and so forth. And so you can come up with a pretty good idea of how much water you're going to need in the future by looking at what you currently use, all right?
Does this have information on, like other landscape, trees, shrubs, stuff like that, or just lawns?
Just lawns in general. You can break things down by type, but it's probably going too far into the details. And we just kind of say as an average, people, use about this much for water in the house and so forth. Yeah. Okay. And so I know we're out of time here, but some information on commercial, firefighting, lawn irrigation, public use, and so forth. And then the other documents are on fire flows and on population growth. And we will continue those on Friday, so it'd be good for you to read through those before we talk about it. Okay? So have a great day, and we'll see you on Friday.
Do you, for homework, do you want us to write something on it?
No, your main homework is the pipe network with the pump. And then I just suggest that you read through this because it'll make when we talk about fire flows and everything a lot easier.
Okay.
Okay. Let me just stop this really fast.
Yeah.